Hello, I'm Simon, also known as Polyhop. In this TouchDesigner tutorial, we'll be looking at how to create a displacement effect using distance maps, specifically focusing on the jump flooding algorithm. We'll be using TouchDesigner version 2023 11600, so if you're using an older or a newer version, it may not work in the same way. Thank you to my Patreon supporters, and a special thanks to my top supporters for helping make this happen. Through my Patreon, you can gain access to project files, vote on future tutorial topics, and more. Today, we'll be looking at how to create this displacement-based warping effect. It uses a technique called the jump flooding algorithm, which we'll look at in a moment. We'll also look at how to create an input with a more angular style, using what's called a Plexus effect. So let's go ahead and first talk a little bit about what the jump flood algorithm is and how it lets us accomplish this. The tool we'll be using today is one from David Braun in his TouchDesigner shared GitHub repository. It's under Tops, and then if we scroll down, we can find jump flood algorithm. We want the jump flood algorithm.tox. The TOW also has some good examples, but the tox is what we'll be using in the tutorial today. The tool itself is originally from Thomas D. Wald that was released under the MIT license and ported to TouchDesigner by David Braun. The jump flooding algorithm itself is an algorithm used in the construction of Voronoi diagrams and distance transforms. Voronoi diagrams are another topic for another time, but the distance transform is what we care about today. It's also known as a distance map or a distance field. What it does is we take an input image. This one is a binary image. And we can think about the pixels where we have 1 in each channel as our boundary or obstacle pixel. And it returns a new image where each pixel now represents the distance to the nearest boundary. So if our boundary, I have on the right a visualization that shows the values of each of these pixels, and the place where I have my boundary is 0, and as I move further away, we get to 7 in the center, but then as I start moving back, it moves to 0 again. So essentially, it's a map of the distance to the nearest boundary pixel. Now we can feed it different inputs, so I could give it a circle. In this case, I'm getting decimal values, so I've switched the view to show a rounded decimal. And you could also animate. Currently I'm just showing the boundary pixels, but it can be a little more useful to look at it on top of the normalized view. One thing I want to note is, let's look at the circle for a second. By default, this comes in with the clamp negative distance on, and you'll notice that my boundary pixels are all clamped at 0, which can sometimes be useful, but in our case, we're going to want to turn this off, and now you can see that we have negative values going towards the center. We still have 0 at that boundary, right at the edge. One other thing you'll notice in this dropdown is we have the option between two different distance calculations. One is Euclidean and the other is Manhattan. It has a slightly different effect. If we change this, you might notice very subtle changes in the output. And actually in the effect that we'll create, you can see a little bit of that as well. It's subtle, and I usually use Euclidean, but both of them can be interesting. The actual difference between these, this green line represents Euclidean distance, which is what we're probably more familiar with. It's the Pythagorean theorem used where you calculate the hypotenuse using the two legs of a right triangle. Manhattan is named after the, like a city organized as a grid, like New York City or Manhattan. Essentially what it is instead of using any diagonals, we're adding up all of the sort of gridded components. So we could add the length of the red, or we could add the length of the yellow or the blue. It's all actually going to give us the same result. But essentially, instead of doing the Pythagorean theorem, we're just adding up the composite of these legs. Now that we've looked at the jump flooding algorithm, let's look at how to use it to create our warping effect. Let's start by creating the input for our jump flooding algorithm. So if you recall, that's white pixels, white or black, like binary image, and we want that to be repeated across all 4 channels. So in this example, we'll start by using a noise top, and I'm going to change the resolution to something like 1080 by 1080. I also want to increase the period quite a bit, so I don't want quite as much detail, maybe even dropping the harmonics down to 1 and dragging the exponent down to 0. I also want to give this a little bit of animation. So under transform, let's just add the Python script abs time.seconds multiplied by 0.1. So this will, I'm paused. There we go. So this will animate our noise a little bit and give it some motion. I also want to now, I'm going to drop an edge top after this. So this is giving us that boundary pixel line that our jump flooding algorithm will be calculating the distance to. And, you can play with how much detail is in this, but you'll see it adds a little bit of detail after we process it. So I like keeping this relatively simple. I do also want to add a circle. And this is just sort of like something I like, but you can play with it or without it. I think it adds a little bit of a consistent form to the output. Let's drop the fill. We want to mimic this kind of line. So I'll add a border width. I'm going to change the unit to pixels and set this to about 4. And then also change the border color to white. Okay, even 3. It's closer. Won't make a huge difference, but here's our input. So the next step is to drag in our jump flooding algorithm talks that we downloaded from David Braun's GitHub. So I'm just going to drag that right in. And we want to plug in this circle to our in1 mask, and we can drop a null after the first output, which is our distance. So looks like it just gave us, we can see there's a little bit of that fade happening right at the edge, but this is a little bit deceiving because right now we're only looking at the values between 0 and 1. If I hit A and then N, you'll see that in this normalized split view, if I right click, you can get this drop down. We are seeing 0 to 12, 11 roughly as our white pixel. So there's a lot more value in here than we can just view normally. One thing I want to adjust on this is I do want to, instead of 0.036, change this to something like 0.36 for both. So it does make a much larger value here, but I think this makes a more pronounced effect as well. And additionally, I'll turn off clamp negative distance. It's not a huge negative value, but what it does do is it gets all the way to like the insides of these lines. So if I did have thicker lines, things like that, we wouldn't be clamping it at 0. One thing I want to point out here that will come into play in just a moment, if I middle mouse button over this top, you'll see that it's a 32-bit float. It says mono. This means there's only one channel, and if we place anything after it, it will default to this format. So that can be an issue if we are trying to analyze it and we want to have more channels afterwards. So just a gotcha that can happen if you're doing something else with this. Keep in mind that it is outputting a mono format. So the next step, we have this nice gradient, but we want to displace our image across that in a way that can be moved in kind of the X and Y directions, up and down and left and right. And so one thing we can do to get that is by using a slope top. So this by default is set up to do what we want. It says a horizontal luminance for red, which is looking at the slope horizontally, and then a vertical luminance for blue, which is looking at the slope vertically using the previous and next pixel. So it looks at the neighbor pixels. Now you'll notice this is black and white. It's still mono. And so the way to fix this is under common. Let's just change our pixel format to 32-bit float RGBA. And now we've got color. If I hit A and N, you'll see our red channel and our blue channel look very similar, but they're a little bit different. And that's because they're analyzing the image in different directions. Great, I'll turn that off for now. And then the next step, I do want to have some kind of source to displace. So you can use any video file that you have handy. You can use your webcam input. I'm going to use just that sort of a time-lapse traffic stock video that I have handy. So I'll create a movie file in top, and if this defaults, that means this was saved perhaps with some kind of input that it remembers. So we can just disconnect that and delete our file, our sample folder here. This is just so that it will default to my assets folder. Yeah, so it's moving a little bit fast. I'm going to drop the speed to 0.5, and also in the image, turn on interpolate frames so that it, if I pause, you'll see every other frame, it's kind of blending or interpolating between adjacent frames. So I'll hit play again. I also want to crop this. It's currently 4K resolution, so I'll just throw a fit top after this, and we will set the resolution to 1080 by 1080. And then also choose fit outside. So we get a nice, no letterboxing. Additionally, I'm going to loop crossfade so that the beginning and the end of the video crossfade. So I'll type 0.05. Sometimes loop crossfade can hang or stutter depending on your computer's hardware or the video codec. So using the HAP codec or an SSD with a high read speed, or ideally both, can improve video playback in instances when it's necessary. Next, we will create a displace top to warp the source video using our slope. So using displace, drop that in. This is my first input, which is the source image. Second input is my displacement image. Now, let's take a second to just set this up so we can see what we're looking at. I'll turn on my display flag, split the screen, left to right, Alt-4, or this drop down lets me look at the top viewer, then right click, display, backdrop tops, turn that off. So it's pretty extreme right now. Let's see what we can do to make it a little bit less wild. If you look at it, we have these, especially in the normalized split view, sort of like artifacts that are showing up at the edges, these lines. So one thing we can do is go ahead and blur that, maybe with our blur top. And I'll bring that all the way up to 32. So now we're getting a smoother transition here, which is nice. If this is heavy on your machine, it can be pretty heavy on the GPU to pull the filter size all the way up. You can bring that down and use the pre-shrink down to something like 2 and then dial that in from there. I'll bring that back to 1 and 32. There are also some adjustments to our displace top we'll want to make. The source midpoint should match our slope, so we can leave that at 0.5. The displace weight, it's a little bit hard to tell, but it this is like the amount of our effect. Actually, this is easier to tell. So maybe bring that down to like negative 0.4. So it's going in the opposite direction. And our UV weight, if we pull that down, it increases the size of the image, whereas if we bring it up, decreases it, and then we'll start to get this hold on our extend. So I will bring this up to maybe 1.5, and then and my displace weight to negative 0.5, and then under extend choose mirror. So that gives us a nice kind of like mirroring effect whenever the image reaches its edge. So we don't ever have, like, if we change this to 0, you can see all of the places where, especially at the UV weight at 1.5. If we bring this up a bunch, we don't get that mirroring repetition, but it also blows the image up. So I sort of like this one at 1.5 with mirroring, but depending on your source input and the resolution of that input, you might play with these settings a little bit differently. So one additional thing I might want to do, we've smoothed this out kind of like spatially, but I also want to smooth it out in time a little bit. When these changes happen, they kind of pop in and out of existence sometimes when, especially when lines go off the side. So one thing we can do is use a simple feedback loop to add a little bit of smoothing temporally. So I'll go ahead and right click and add, let's see, what do we want? Let's add a switch. So I'm going to use the blend between inputs option on our switch here to mix between feedback and our current input. So I'll add a null after this. We can call this end feedback. And then I'll also add with the middle mouse to split feedback. And then drop this into our switch. So currently nothing's happening. We need to point our end feedback at our feedback top. So I'll drag that onto target top. And what this does is each frame, our feedback top, instead of taking anything from the input, it is taking the previous frame from the target top. So this is like our last frame and our new frame. And what we can do is change the blend. So I'll turn on this blend so that we're getting more of our previous frames, like mostly our previous frames, and adding in a little bit of our new frames, which will gradually move us towards whatever this input is. So when something pops into existence, it takes a few frames for it to kind of move towards and blend towards that target. So if I set this to something like 0.85, now when things appear, it's happening. You're getting a smoothed motion. If this was 1, it would actually stop because that's saying I only want my previous frame, and my previous frame is never going to change. If I bring this down a little bit, it'll still, move a bit slower, but have more gradual changes. And then if this was 0.2, we'll still see almost none, right? So even I think 0.5 is really the spot where you'll start to see a little bit of effect. And I like it closer to 0.85, 0.9. You can dial this in as you choose, but essentially this is it for the jump flooding displacement effect. Now that we have our jump flooding effect, I want to show us how to create an additional input that's a little bit different in quality. Initially, I showed this version, very angular in quality. And if we look at what the input looks like, this is what we'll be looking at creating. This is an effect often called Plexus. The specific approach we're using is based on a Paqueta 12 tutorial from a few years ago that I'll link to in the description. It's created by taking a set of points and connecting them based on proximity. So if they're within a certain distance threshold, you draw a line, and if they're outside of that threshold, you don't. So let's go ahead and take a look at how to create that. All right, jumping back to where we left off, let's go ahead and move over to the left and give us some space. And we'll start with a noise top. This is what we'll use to generate our initial points. Now I want to set this to 3x3 for our resolution. In this case, we don't want a lot of points. You can certainly add more, but the density of this pattern, it doesn't really need to be that complex to create interesting warps. When this is very dense, sometimes it's harder to see what's going on after you run it through our jump flooding. So let's start with 3x3. Let's change the pixel format to 32-bit float. I also, under noise, want to change this to not monochrome. So toggle that off. We should have different channels for our red, green, and blue for our X, Y, and Z positions. I also want to bring the period down to something like 0.02. We want our points to, kind of the density of the noise to be pretty high so that, they're pretty unrelated and scattered in their motion. We also want to set our amplitude to 1.3 and bring our offset to 0. These values relate to our camera settings that we'll use later. I also want to give this some animation. If I hit A and then V, we'll see our 9 points. And under the transform, we want to animate this translate 4D parameter. It's grayed out because we have 3D noise. So let's go ahead and choose Simplex 4D. And then under transform, I'll use a Python expression abs time dot seconds and multiply that by let's do 0.03. So you can see that it is gradually animating our points in 3D space. All right, so the next step, let's add a limit top. We want to use this to quantize our points. In my example, they jump from kind of like on a grid, which gives us a more like consistent angles and things like that. So I'll use round under quantize value, 0.3, and then A and then V. You can see our points are jumping around discontinuously. Cool. So under common, let's choose viewer smoothness nearest pixel. And I'll do the same for my initial noise. I'll be doing this throughout. One, just it makes it easier to see what's going on. And then in a couple instances, the input smoothness needs to be nearest pixel or you get interpolation. So it can mess up a couple of our operations. Now we have our points in a 3x3. I'm going to use a tool under the point cloud section of the palette called Point Repack. We'll drop that in and close the palette for more space. This lets us repack our 9 points into a 9x1 resolution. Now, I want this to be adaptive. If I do decide to increase the number of points, I'm going to base this resolution on the width and the height of this first input. I can do that with me.inputs, which gives me an array of all the inputs going into this operator. And in the square brackets, I do need to tell it to choose the 0th input. Otherwise, even though there's just one, I still need to tell it to select that input. I'll type .width, and that will give us the width of the operator that's plugged in. Now to get all the pixels, I'll multiply that by that same expression that I copied. So copy and paste that, and then just change this to height. So it should change if we did change this number. You'll notice that the resolution automatically adapts. One word of caution is be careful with how you change the resolution of noise too, since this will change dramatically based on that. It can lead to issues such as running out of GPU memory, in which case TouchDesigner will typically crash. Next, let's use a fit top. And we're going to set this also to that same expression that I have in the clipboard. And I'll just set that to width and width. So we have 9 by 9. Now, let's also choose fill for our fit. And under common, make sure we choose nearest. This is the most important instance. If you don't choose input smoothness nearest here, it will interpolate values and you'll get incorrect results. Now, we have our points, 9 of them, and they're also kind of like duplicated along every row. So our columns are essentially our 9 points. The reason for this is we'd like to compare every single point with every single other point. So we can create a flip top and flop this bottom left, so essentially rotating it, but also rotating the dimensions, nearest pixel. So now we have another set of points, except now our points are in rows instead of columns. So to actually get, say, a vector from point, let's say this is our point A, and point B is our flip. To get the vector created by those 2 points, we can subtract them. And now we have a set of, this is essentially a set of vectors. They have magnitude and direction. And each pixel represents the vector created by one of our points and another one of our points. So you'll notice that we have 0 along the diagonal. The vector created by point 1 to 1 is going to be essentially nothing. It's not going anywhere. But now we have 1 to 2, 1 to 3 on that second row, 2 to 1, 2 to 3, and so forth. So we can now use these vectors to start calculating distances. Let us add a null after this, and we'll name this dir for direction. Nearest pixel for our viewer. I'll make it red so we can visually see it. Another null after our fit to. So we do want the position as well. We'll use this as where we draw our lines. Nearest pixel. The direction we'll use to orient our lines. And the last thing we need to do is calculate the distance, both for scaling the length of our lines and also to determine if we draw them or not based on their proximity to other points. So yeah, we've got plenty of room here. I'll give a little bit more space. And then let's use a math top, which has under combine channels, the option to calculate length. Now, let's just to see this better, nearest pixel, you'll notice that our length is being calculated in the red channel, but let's, under op, not look at our alpha. It is 0. It doesn't affect anything, but it's good practice. And then combining channel output, as we toggle these on, now you can see it's copying my length across all channels. One thing I want to point out is the symmetrical quality of this. So you'll notice that we have 0 along the diagonal. That makes sense. No length when you're comparing a point to itself. But these point 1 to 2 and point 2 to 1 also should have the same length. So that starts to explain why this has this diagonal symmetrical quality. One thing that Paqueta 12 does, which I think is really clever, is to not only mask this bottom diagonal of redundant points, but he also uses some UV remapping to kind of repack this whole texture into a set of points that are a little more efficient. We're not going to go through that process in this tutorial, but I definitely suggest checking out the original that I'll link in the description so you can see how that might work for use cases with more than, say, 9 points. So now that we have our distance, let's threshold it with a threshold top, aptly named. Let's use greater for our comparator. Luminance is fine since we have set all of the channels to be the same. We also can dial this in a little bit, the threshold. I think mine was 0.76, though changing this will affect how many lines are drawn. We'll want to multiply this by our distances, since this is essentially a binary image, 0 or 1, based on whether the distance is above or below the threshold. I'll also go ahead and make this nearest just for viewing purposes. I'll use a composite top to compare these, or multiply them. And this is because I also, changing this to nearest, I also want to mask that bottom diagonal just for good practice. It won't really affect performance too much, but it's just a good habit. We can do this with a ramp top, and we'll set this to radial. We're looking to create a diagonal mask that's white on the top diagonal and black on the bottom. You'll notice if I change the phase in the negative direction, we're close to right here, like negative 0.38, but to be more exact, negative 0.25 or negative 1/4 gives us directly down, so negative 3/8 is that diagonal. So I can just type that in, negative 3/8. I'm also going to position the ramp at 0.5, 0.5, so the origin is the top right. And I'm going to set this to step and pull this stop over a little bit. So now we have a white and black mask that's diagonal. A couple additional steps we need to do here. One is, you'll notice this anti-alias value. If we look at these values with A and N, you can see there's a strip of gray where it's aliasing, or attempting to anti-alias. So it's actually, we want it to alias. So let's set this to 1, and now we'll see a sharp pixel line. And now let's plug in our math here, just for the resolution. Set resolution only, common, nearest, and we have ourselves white pixels in that upper diagonal. Those are the only lines that we care about, since the rest are either 0 or redundant. We can go ahead and just plug that into our multiply here, so that now we only have those upper diagonal lengths that are also within our threshold. Last, let's create a null and just call this length, and I'll make that red. So now we have the 3 pieces that we're going to need to draw our lines. Let's continue with the geometry for our instancing network. We'll start with a line sop, and I'll make this 1 unit in the positive z direction. So instead of 0 to 1 in x, let's go from 0 to 1 in z. I'll also create a geometry comp by right-clicking the output. And here's where we can turn on our instancing. So I'll turn on instancing, start by dragging position to our translate op and type RGB. So now we should see our lines jumping around based on our noise. We also want to scale this based on our length. So I can drop, let's keep that kind of in view, drop length on scale. And I want to scale this based on the Z only, using the R, since that's the only length we care about scaling. Lastly, we want to rotate these to our direction vector. So under instance 2, we have our rotate to vector. I'll drop on dir for the op and type RGB. And it does something. It's not perfect yet. A couple things we need to change. One is the forward direction is currently negative Z, but we're going in positive Z. So one way to change this is just choosing positive Z. You could also change the line. Both work. And still not quite right. And what this comes down to is this rotate order. Usually when we're using rotate to, I use rotate, then rotate to vector. I rarely am using this first option. And this gives us what we're looking for. So you'll see that our points are essentially being connected based on their proximity. So to finish up our instancing here, we do need a rendering network and a couple other pieces. So let's create a line mat for our material. We can just drag that onto our GO1 and choose param material to put that into the material parameter. And I'll make this the same width, so 4. And under line, I'll set this to 1 and turn off specify line color. I think my example, I have this set to 0.8 still, and then I use a math top to round up, but setting this to 1 is a little bit easier. Let's also create a camera and a render, so a top, so camera and a render top. Go ahead and set this to 1080 by 1080. Now there's a little bit of it's a perspective camera, but my effect originally I'm using an orthographic view. That way you'll kind of see the difference here. When we're looking at it straight on, anything that's in the Z axis, we're not seeing that kind of like angle based on the perspective or the vanishing point. I also can adjust this ortho width a little bit. So my example is 0.6. You'll see that's the width of the render is now 1.6, so it's fixing that orthographic width. And yeah, we're pretty much there. I can, scoot this over a little bit and then just for now swap that out for my input and start to see how that changes the output as it warps my video. So one additional thing, similar to the way that I add the circle for the noise-based lines, I found adding a rectangle was a nice touch in that it gives it a little bit more context. This is totally, up to you, of course, but can bring that up a little bit in size, bring the fill alpha down. We'll set the border to white and for border width, maybe 4 pixels to match. And so now we always have that frame. I found that kind of gave it a nice structure and continuity, even when the Plexus effect was doing something less consistent. All right, so here we are with the finished effect and a couple different options for inputs. Now, of course, you can try lots of different things with this. I think there's a lot to be had. Of course, generating different sort of white and black inputs that feed into this. Make sure that they are 0 to 1 identically. in every single channel, or this won't work correctly. You can, of course, play with some of the blur and the slope parameters and feed it lots of different inputs, because it really creates some different effects and feelings based on the input as well, whether this is a camera or a movie or something that you've generated either in real time while you're, doing this, the rest of this, or maybe it's pre-rendered content. So lots of options to be had here. I hope this gave you some good new techniques, and thanks so much for watching.